Hello world, and welcome back to an introduction to artificial intelligence. Now, so far in this class, we've seen many different ways that we can give information to AI, and AI can learn from that information. Today, we're going to flip the story a little bit and talk about how AI can generate information of its own. We're talking in particular about a kind of AI known as generative AI. So when we talk about generative AI, what are we really talking about? Well, here's our representation of AI here. And generally, we've been thinking about AI as something that needs to be fed data, where data is provided as input to AI. But today, we're going to be talking about strategies we can use to allow AI to produce or generate some data of its own. So what kind of data might be the output of our AI? Well, we might want AI to be able to generate text, to be able to write words and sentences and paragraphs. But we might also want AI to be able to generate other kinds of media too. Maybe we want our AI in this case to be able to generate images, for example, or to be able to generate sound, or to be able to generate video. And so these are the kinds of things that we're going to be exploring today, thinking about what would it take to get AI that's able to create content of this kind, to be able to create text and images and sounds and more. And let's start with the world of text generation. We were talking recently about how we can use AI to understand our natural language, and we can build on those ideas to think about how we might get AI to become very good at generating text of its own. And in what kind of context might that appear? Well, it might come up in situations like question answering, something we've explored a little bit before, where we might pose a question to AI, something like, what is the longest river on Earth? And in order to understand and analyze that question, we talked about this idea of tokenization, where tokenization allows AI to be able to understand language, not by taking in the entire sentence all at once, but breaking up some piece of text into individual pieces. You might break it up into characters or words or smaller pieces within words. For now, we'll go ahead and tokenize this by words. And so we'll split it up into individual tokens. What is the longest river on Earth? And then another token for that final punctuation mark. And then what we'd like for AI to be able to produce for us is to be able to produce the answer to this question, which will also take the form of individual tokens, to be able to produce an answer like the longest river is the Nile River, for instance. And we've seen some strategies we can use to allow AI to be able to predict a token, to be able to generate a token as the output of a neural network, for example. But how are we going to deal with these longer sequences? We want AI to be able to generate complete sentences, maybe even multiple sentences, and make sure that we still have a way of doing that. Well, let's go back to our story of this language model we were using in order to analyze something like this question. If we take all of these tokens and we provide them as input to our language model. Remember, this is an AI model, likely some kind of a neural network, that's been trained to take a bunch of tokens of text as input and then produce an output token. And that output token represents what is the token, or in this case, what is the word that we think is the next word. So if we provide the question as input to the language model, like what is the longest river on Earth, then ideally the output token might be the first word of the answer to that question. So if we give all of these tokens to the language model, we might hope that what the model is able to come up with is something like the word the. That might be the first word of the answer. But of course, that's not the complete answer. The answer we're looking for is a bigger sentence. So now we want to know, well, what is the second character? Well, how would we do that? If we just gave the same input to the language model again, we'd probably still get just the same output, the word the. So instead, what we might do is take that output token, the word the, and go ahead and turn that into another input to the language model. Now we're providing as input to the language model all of the same tokens from before, all of the tokens that were part of the question, plus this first token of the answer that was produced by the language model itself, but is now being provided again as input to the model. And so now we're saying, here was the question, and here's the first token of the answer. Go ahead and try and predict what do you think the next token of the answer is going to be. And in this case, if we give this to the language model, what we might hope is the language model will come up with something like the token for longest, the second word in this response. And then we can repeat that same process. Anytime we want to keep generating text, we can generate that text one token at a time. I can say, all right, that word longest that was just produced by the language model, let's go ahead and make that an input to the language model too, provide all of that input back into the language model, and have the language model then produce as output something like the third token, in this case, the word river. And so we could keep running that process, generating one token at a time until we've generated our complete answer. And this is the basic idea of how generative AI is able to generate text. But how is the AI actually trained to do that? Well, recall that we trained that AI using data. And data in the context of text took the form of examples of pieces of text in the English language, in this case, that we were using in order to have AI understand the patterns in language, to understand what words tend to appear near each other, and to be able to get good at performing prediction tasks like these. So how could we take data in the form of like a book or other kinds of text and turn it into something that AI could use to learn to predict from? Well, here's a sample of some text from Alice's Adventures in Wonderland. And again, we can use the same process of tokenizing this text, splitting up this text into individual tokens, where we might have one token for each word, for instance. And then, using this as our training data, we can come up with problems that AI tries to solve. We can say, all right, given just this very first word, Alice, can you, the AI, predict what the next token should be? Could we get AI to predict that the word was comes next? And if we gave AI these first two words, Alice was, then have AI learn to try and predict this third word, the word beginning. And then we can give AI these first three words, Alice was beginning, and see if AI can come up with that fourth word too. And so inside of this text, we have many, many different examples that we can use to train AI. We can say, give all of these initial tokens to the AI, and see if it can come up with what token comes next. And if it gets it right, great. And if it gets it wrong, then we can use that to train the AI a little bit more. We can say, all right, update the weights inside of your neural network so that you can do a better job of trying to do this kind of prediction task in the future. And by giving AI more and more data, we can allow AI to get better and better at performing this kind of prediction task of like taking all four of these words and saying, OK, the next word is probably the word get. Or after all of these words, the next word is probably the word very. And we can do that step by step in order to understand and predict what the next token might be. But that's really all AI is doing when we're thinking about generative AI trying to produce answers to questions. It's all going into this neural network and predicting what the most likely next token of the response might be. There's no guarantee here that the answer is necessarily the right or the correct answer. It's all just a matter of probability and based on whatever data AI happened to be trained on. And so what that means is that when you ask a question to AI and you get back an answer, what you're getting back is what AI thinks the most likely sequence of words might be in order to be a good answer to the question. But there's certainly no guarantee that that answer is factual or completely correct. And we call this potential problem this problem of hallucinations that can happen in the world of generative AI, where generative AI might come up with something that is in fact not factually true, something that happens to be wrong. But when that happens, it's not something fundamentally different going on inside the AI. It's not like a bug in the AI that could easily be fixed, for instance. It's just fundamental to the nature of what these kinds of AI are doing, which is that when they're generating text, they're making a prediction as to what they think is the most likely thing. And sometimes they might be right, and sometimes they might be wrong. And so again, it's something that we as users of AI need to be mindful of, that we have to treat this kind of AI differently than we treat a calculator or a dictionary, in the sense that we need to be concerned about what happens when it gets it wrong, to what degree are we trusting AI, and how are we integrating AI into our lives, if at all, in order to decide to what extent we want to believe or not believe the output that we might get from AI as well. And so, sorry, I got distracted. This screen started spinning. I don't know if that's a problem. It's back now. OK, no worries. I think we can keep going. I had wrapped up this section, and then I'll just continue into the next section, which will lead us to this next slide. So let's take a closer look at what might actually be happening inside of a neural network when we have this neural network try and predict what the next token, what the next word in a response might be. So I'll go ahead and show you an example of a neural network. And remember that the output of the neural network, that very final layer of that neural network, is going to represent what word or what token we think comes next. So each one of these output units or neurons in our neural network represents one different token. And ideally, what AI is going to try to predict is, I think there is an X% chance that it's going to be this token that's next, or a Y% chance that it's some other token that's next. So if I'm trying to do something like ask AI to come up with the longest river in the world, then my hope is that one of these output neurons, and usually there are going to be many more than just what you're seeing here on screen, is going to be like the word Nile, for example, for the longest river. And the value associated with this is going to be the output of this neural network. It's going to be what is the likelihood that AI thinks that this is the next token that we should generate in this case. And maybe in this case it thinks there's like an 82% chance that the word Nile is the correct next token. Odds are that AI is never going to be like 100% sure that this is definitely the right next token. Language has variability and uncertainty to it. So it's going to have some sense that this might probably be the right next thing, but oftentimes there might be multiple choices for what might be a reasonable next thing to say in any given sentence. And so Nile might be the most likely option, but maybe there are other options that AI thinks could also complete the sentence, or might also be reasonable answers as the next token to predict. For example, somewhere else in this neural network might be an output unit corresponding to the Amazon River, for instance, and maybe that has a slightly different probability for what it thinks is likely or not likely. And based on this particular neural network, the way that it was trained, the data that it happened to be trained on, this neural network seems to know that Nile, that's a much more likely answer than the word Amazon. But that might vary depending on what kind of data the AI was trained on. If it wasn't trained on a lot of data that had information about rivers and how long they were, for example, maybe these probabilities wouldn't be as strongly in favor of one versus the other. The numbers might be a little bit different, where maybe it's only slightly more sure that it's the Nile than the Amazon, for instance. And it's not always going to be the case that AI is going to predict just whichever one is the most popular word or the most likely word as the next thing. This is going to be treated as kind of like a probability distribution, that maybe 80% of the time, AI is going to pick Nile as the word to say. And in this case, something like 10 or 13% of the time, AI is going to pick Amazon as the next token that it might want to say. And so AI doesn't always choose the thing that is definitely the most likely. And why is that? Why wouldn't AI just always pick the thing that is definitely the most likely? Well, the reality is that natural language, because of its uncertainty, we don't always say the thing that is the predictably, statistically most likely next thing to say. If we did that, language would be quite predictable. Conversations would probably be quite boring because there would never be any uncertainty, anything unusual in language. That language naturally has some of that occasional uncertainty, some of that occasional thing where you might say something that's a little bit less common. And so with AI too, we're going to have a similar situation, where we're not always going to predict the most likely thing. Sometimes we might pick something else instead. Now, many language models give you the capacity to control this type of behavior. To what extent do you want AI to always pick the most likely thing and maybe be a little bit more boring in its responses and not be as creative? And to what extent do you want AI to be a little bit more creative, sometimes pick the less common words, and then you might get some more creative output? And we call that kind of control the temperature of the model. The temperature of the model describes how often are you just always picking the most likely thing, and how often are you going to be a little bit more creative and sometimes choose between options that were originally a little bit less likely. And so if we call this like a medium amount of temperature, for instance, if we were to lower that temperature all the way, at a really, really low temperature, we're saying just always pick the most likely thing. If Nile is the thing we think is most likely, just always pick that token again and again and again. And that might help you in this case to get a correct answer, but that language might not feel very natural, because in reality, our own language is not always just statistically predicting the most likely thing all the time. And meanwhile, if we raise temperature all the way to the maximum, well, that's basically saying don't care at all what things are more or less likely. Just treat every word the same. Just randomly pick a word. So that will be ultra creative. It'll be very creative. It'll choose a bunch of random things, but it might not make a whole lot of sense. It might be more likely to make factual errors, for example. And so oftentimes we want something in the middle. We want it generally choosing the words that it thinks are most likely, but we don't want it to be boring and just always picking the most likely thing every time. We still want it to feel a little bit natural and have a little bit of creativity to language in the way that human creativity also has that kind of variability to it as well. So those kinds of controls do exist in some of these language models too. So let's talk a little bit more about then how can we get a language model to increasingly likely produce a good response? How do we get AI to be able to generate an output, generate some text that we want it to produce? Well, what's an example of an input that I could give to this language model? Maybe I'm visiting Boston, and I would like an itinerary for my trip to Boston. What should I do while I'm in town? And so I might have what we call a prompt, some input to this language model like this. Write a 3-day itinerary for a trip to Boston. And that'll be the input to this language model. And ideally, the language model will produce as output some kind of itinerary, something for me to do while I'm in Boston, for instance. But this was a relatively simple prompt. I described what I wanted, write a 3-day itinerary for a trip to Boston. But remember that what a language model's output is going to be depends very heavily on what the input is. We talked about mechanisms last time like attention, where AI can pay attention to particular parts of the input and figure out what to pay attention to in order to do a better job of trying to produce the output. And so there's an importance that's placed on what this input is. Depending on what the input is, that really guides what the output is going to be. And so if we're thoughtful about how we craft this input, we can often get an output that's closer to the thing that we might want. And we call this kind of technique prompt engineering, the idea that this prompt, this input to this AI language model, can be modified, can be molded in some way where we can adapt that prompt to be very specific to what we need, such that we increase the likelihood that the output is the output that we want to. And there are many different prompt engineering types of techniques, and we'll talk about a few of them now. One approach is just to be more specific. I've said, write a 3-day itinerary for a trip to Boston, but I could have also added something like, I'll be there in June, and I enjoy museums and sports, for example. And so now I've added a little bit more specificity to the prompt. And why is that helpful? Well, now when this language model is running, when it's performing its attention calculations, figuring out what words to pay attention to and what types of things are the most likely thing that we should generate that are going to do a good job of mapping to that input, well, now it can pay attention to things like the word June. So we can say, OK, what are the things that are worth doing in Boston during the summer? And it can pay attention to the things that I like, words like sports and museums. And maybe it can find other examples in its training data of things that are related to Boston and sports and museums as things to suggest to me as well. So that's one kind of input that I might try to provide to AI instead. Another strategy would be to give AI more explicit instructions, tell it in more detail what should you do, like brainstorm a list of possible destinations, evaluate them on cost and transit accessibility, and then plan the itinerary after that. And by being a little bit more specific, we can get AI to follow these steps a little bit more directly so that hopefully I get responses that are closer to what I want. If I really care about transit accessibility, for example, then that's something I can tell AI, have it bias its answers in that direction by, again, having the language model pay attention to the language of the prompt to help it do a better job of producing the output. Another type of thing I might do is provide an example. I could say, you know what? Here's an example itinerary from a recent trip that I took to New York, and then provide that example itinerary. And now the language model has an example that it can pay attention to. It can understand the structure of the itinerary that I tend to like. It can understand the types of activities that I've maybe tried before in other locations. And it can use that information to guide the way that it tries to produce a response as well. So sometimes changing the input can be a way to help us get a better response from the language model. And one other thing we could imagine doing as the designers of the language model is thinking about how do we evaluate the output of the language model? How could we look at the output of the language model and then use that output to try and make our AI better in the future? Because from the same input, you could imagine different reasonable outputs that you might get as the answer to a question. So if we go back to this example, where my prompt in this case was, give me a 3-day itinerary for a Boston trip, well, different AI models might give me different responses. So here's one AI and one response that it might provide. And here's a second AI and the response that it might provide. And how do we know which one is better? Well, one way we could do that is just present it to a human. Ask a human to look at these two responses and judge which one is better, which one is worse, how good do you think this response is, how good do you think that response is. And using that kind of human feedback, using data from humans where they look at these answers and decide which ones do they think are better and worse, we can train a different model. Not this language model that's generating text, but a model that we might call a reward model. And so what is the reward model doing? Well, what the reward model is doing is it's taking AI-generated text as input. That text is going to be the input to the reward model. And what the output of the reward model is going to be is it's going to be some kind of judgment as to how good or bad do I think this AI-generated text is. And it might be a rating, for example, in this case on a 5-star scale, where we're saying here's how good or bad we think this text is. So we could start to train this other model, this reward model, that's going to get very good at looking at an AI-generated response and saying, do I think this is good, or do I think this is bad? And that model is going to be trained based on data, like many AI models are. And the data it's trained on is human feedback, humans deciding this response is good, that response is bad. And using that, we can get a sense for what is the kind of response that humans tend to like. And so then we can use that reward model to try and make our language model a little bit better. And we call this kind of technique reinforcement learning from human feedback, or RLHF. where we've seen reinforcement learning before. We saw when AI was learning to play games, for example, it could play a game, and every time it crashed or every time it did something good, it was able to learn from that experience and get better. So it was learning from its own gameplay in that case. In this case, we're talking about reinforcement learning, where you're learning from human feedback, where you produce a response, and depending on whether human feedback tends to think that response is good or bad, we can learn from that too. So here then is what that architecture might look like. We have our language model, and again, we feed as input to that language model some kind of prompt. So that prompt is the input to this language model. And then what the language model does is it produces a response. And previously, we might have said that was the end of it. It produces a response, the job is done. But now that we have this reward model, and remember, the reward model takes an AI-generated response as input and tells us how good or bad it is, we can then feed that response into the reward model and have the reward model judge how good or bad was this response. And based on what we learn from that reward model, that can then be fed back into the language model as information used to train that language model. So we can make the language model better in the future because the reward model is saying this response was good, do more of that next time, or that response was bad, do a little bit less of that next time too. So these strategies then can be used to try and make AI better at solving those sorts of problems. Now, in order to deal with this problem of hallucinations and AI generating things that we don't want, we need to think about where AI is even getting its information from. Remember that AI is trained based on training data, information like books or articles or documents that it has available to it that are used in order to train that AI. But maybe we want AI to be able to work with more information than just that. If I want to ask AI information about my own data or information about myself, that data might not be part of the AI's training information. And so it might be difficult for AI to be able to accurately answer those kinds of questions. We might want AI to be able to reference information in my own documents, documents that, for example, were not part of the AI's training set. I'll pause here and pick up from there. I need to think about how I want to do this demo, actually. So what other strategies can we use to try and get AI to do a better job of producing text that we want? Well, we can start to think about other types of questions we might ask AI. And maybe I want to be able to ask AI about information that I care about, information that might be in, say, documents on my computer or emails in my email inbox, for example. But if I were to ask AI information about documents that only I have, that are only on my computer, for example, AI is probably not going to do a very good job of answering those questions, because AI can only answer questions based on the information that it knows, based on information inside of its training set, whatever text that AI happened to be trained on. That's the information that AI is using when it's figuring out how to construct a response. So if I have documents on my computer or emails, for example, and maybe I have many of them, and maybe the correct answer to my question is somewhere in my email inbox, well, then we're going to run into some trouble. That if I have like a whole bunch of emails and the answer to the question I'm asking AI is in one of these emails, how is AI ever going to be able to answer that question? Because that particular email wasn't found inside of the training set for AI. So what's an example of this? Imagine that I were to ask AI something like, what time do I need to arrive at the station for my train on Friday? Now, where is the answer to that question? Well, the answer to that question isn't in AI's training data. Nowhere in AI's training data is there a document saying, this is the time that I need to be at the train station on Friday. Instead, that information belongs to me, that I have here a whole bunch of information. Maybe this represents your computer's hard drive or your email inbox, for example. And if I take a look at the information in here, I have a whole bunch of envelopes here. Maybe each one represents an email. And in one of these envelopes is information about what time I need to arrive at the station for my train on Friday. But this is not something that AI ordinarily would have access to. So what can we do here? Well, we have a few different strategies. One strategy would be to say, all right, well, the prompt is the input to AI. The prompt is the information that I provide to AI that AI is then using to decide how are we going to generate a good response. So why don't I just add to the prompt? I'll go ahead and take like all of the emails in my email inbox and everything on my computer, and we'll make that part of the input to AI so AI can figure out what to pay attention to and how to figure out what's the correct information that I need in order to produce a good output. But we might run into some problems here, because odds are I have a lot of information on my computer, not just these, but everything in all of these other drawers and any other filing cabinets that I might have. And so that's going to be a lot of information to go into the prompt. Oftentimes there are limits on how long a prompt can be, and AI might struggle more as those prompts get longer in terms of figuring out what to pay attention to. So ideally, what I'd like to do is just provide AI with the most relevant information. If I can identify that, you know what, this is the envelope that contains the information that AI cares about, I can give this envelope to the AI along with my question, and now AI can look at the question and like the contents of this document to be able to figure out what the correct answer might be. And so this is going to be the type of problem we'll explore next, is how can we get AI to not just use its own training data, but also use other kinds of information, documents that I have, documents that my organization has, in order to learn from that information and figure out how to use that information to be able to produce a good response to a question. So I'll go ahead and put this away for now, and we'll talk a little bit about how we might go about doing that. So imagine that one of these emails might be the email that contains the answer. So this email, for example, might be an email that says, you know what, this is my train ticket sales receipt. It tells me what time my departure time is for my train, and therefore that information is information that I could use to give to AI to help it figure out when I need to be at the train station. And so what I might do is take the contents of this email and make the contents of this email part of the prompt, part of the input that I'm providing to AI. So I could say, in the prompt, use the email content below to help you answer this question, then take the content of this email and just make that part of the prompt now instead. So what I'm giving to the AI is not just this initial question, but I'm giving it all of this content as well. Now, it would be kind of annoying if I had to do that manually, if I had to go through my email inbox, find the right email that has the right information, copy the content of that email, paste it into the prompt, and then give it to AI, because at that point, I could have just found the email directly and used that information myself. But I've had to do a fair amount of work in order to do this. But ideally, we can have some automated way for computers to be able to do this kind of work, for a computer to be able to take this question, figure out what document, what email, what file is relevant to that question, and then automatically include that as part of the prompt that we give to AI. And we call this retrieval augmented generation, or RAG, this idea of we're going to generate text, but we're going to augment that generation process, or add to that generation process, the retrieval of information, the ability to access documents that I care about and include them as part of this AI generation process. And so how could we do that? How could AI try and find the documents that are relevant to the question that I happen to be asking? Well, remember that we've talked before about how every word we could translate into an embedding, some set of numbers that represents the meaning of that word. That we took like the word breakfast, for example, and we had AI turn that into numbers, numbers that were used to represent the meaning of the word. And the idea behind how we generated these embeddings was to say that words that have similar meanings should ideally have similar embeddings. That the numbers used to represent the word breakfast should be very similar to the numbers that are used to represent a word whose meaning is close to the word breakfast. So if, for example, I had the word lunch, that too could have an embedding. And ideally, these numbers are similar to the numbers that we got for the word breakfast, whereas a different word, like the word departure, for example, that might have a different set of numbers altogether that are used to represent it. Well, just as we can find embeddings and have AI come up with embeddings for words, for tokens, We could imagine doing the same thing for sequences of tokens, for sentences, for example, where I could say, the meal is scheduled for 12 p.m. Well, let's have AI come up with an embedding for that, a set of values that represents the meaning of this sentence, such that if I had another sentence that had a similar meaning, something like lunch will be at noon, then ideally, the embedding for that sentence, a set of values we use to represent that sentence, should be similar to each other. And if there was a different sentence that had a very different meaning, the train leaves at 10:30, well, then that should have a different embedding altogether. And that should probably be more different than the embeddings for these first two sentences. And so why is that helpful? Why is it helpful to take sentences and be able to turn them into numbers? Well, if I can take a sentence, a sequence of text, maybe think of that like a document, and turn that into numbers, well, then what I might be able to do is do something similar for an email. And I could take an email or some other file or document on my computer and just turn that directly into some sequence of numbers, some embedding to describe the meaning of that email. But the reality is that an email might be long. There might be lots of information inside of the email across multiple paragraphs, for example, and maybe each sentence means a little something different. And so it's hard to take an entire email and capture the meaning of that entire email in just a single embedding. So instead, what we might do is split up the email, split it up into different chunks, different sentences or paragraphs or a couple of sentences. I can decide how big I want each chunk to be, and just translate each chunk then into an embedding. And so I end up with a whole bunch of these embeddings that are describing the meaning of this email, that are numbers that are used to describe what this email means. And anytime we have a sequence of numbers like this, a sequence of numbers that are grouped together, in mathematics we tend to call that a vector, a sequence of numbers that are all together. And if we have a whole bunch of vectors that are being used to describe the meaning of this email, I could put them into a database, something that we tend to call a vector database. And so the way to think about a vector database then is it's a database of a whole bunch of documents or segments of documents being stored based on their embeddings, based on, in this case, on what it is that those documents happen to mean. And so why is that useful? Well, if now I have a database where I've stored a whole bunch of documents, like parts of emails that are defined by what it is that part of the email means, then when I ask a question, like what time do I need to be at the train station, I can take that question and turn it into an embedding too. I can turn that into some sequence of numbers that I could imagine being in this vector space, plotting somewhere in this coordinate space, for example. And then I could ask the question, all right, which documents, which emails, which portions of an email have a meaning, have an embedding that is very close to my question? So whatever question I asked, which documents look like they might be relevant to that question? And they look like they might be relevant to the question because they have similar embeddings, a similar meaning to the thing that I'm asking about. And if I can find a document whose meaning might be similar to that question, well, then maybe that document is something that I should take into consideration when trying to answer the question. And so the process as a whole now looks like this. I pose a question to AI. I say, what time do I need to be at the train station? And then what AI does is it takes the documents that it has access to, and these are documents that I need to give AI access to. I need to say, OK, go ahead and take all of my emails, figure out what the embeddings are for different parts of the email, and then figure out, all right, which part of that email looks like it's most relevant to the question, which one has an embedding that's really similar to the embedding of that question. And if I can find that email, then I can augment my prompt with the contents of that document. I can say add to the prompt, include this information, so that now AI can hopefully do a better job of identifying that. And that works in this case. And as the database gets bigger, I've got more information that I potentially need to look through. And maybe sometimes I find the closest one, but in a big database, often for efficiency's sake, we don't always care about finding the closest document. Sometimes we'll just find a document that's at least somewhat close to the question that we're trying to ask. But the hope here is that we're augmenting this process of trying to generate language via the use of these documents to be able to give AI the information that it needs to be able to produce a good answer. And I didn't have to do the work myself of saying, here's the email you should use, here's the file that you should use. We let the computer take care of that. We let the computer figure out what's relevant and provide that as input to AI. So this kind of retrieval augmented generation, that can be quite useful for helping language models get access to good answers. But there are other tools you might imagine language models wanting to be able to use as well. And so sometimes when we provide a prompt to AI and we get some kind of response, it can be helpful if that language model has the ability to interact with other tools. And a lot of modern language models have this capability too, where if you give a language model access to a web browser, well, now that language model, instead of just relying on the information that it has inside of its training data, the language model could also do a search on the internet to be able to look for particular information and maybe get back some text that it can include in its analysis that it can pay attention to be able to suggest a good answer to you. Maybe we also give the language model access to a code interpreter so that it can write some code and see what the response to the code is. So if I need a very precise mathematical algorithmic response to something, we could give the language model the ability to solve those kinds of problems too. Or maybe we give the language model access to an entire database of information that it can query and figure out answers to questions for too. And in other cases, we might just give language models access to our computer. We know that AI now has the ability to look at images and see what happens in that image. We could give AI access to our computer so we can see the contents of our computer screen and identify what options to click on and what options to use inside of our computer as well. And with all of these tools, we have to think about the implications of them, right? If you give the language model access to your computer, well, what if the language model does something you don't want it to do? What if it accidentally thinks some button is the right one to click on and you didn't want AI to click on that button? Well, now you might be in a little bit of trouble. So you have to be mindful of the safety, of the privacy implications of any tool you give AI access to. But when you do give AI access to those tools, then it has the capability to use those tools to potentially do a better job of producing a good response to you as text. And so there are lots of these strategies that we can use to allow AI to do a good job of trying to generate text. But text is only one of the kinds of data that we might want AI to generate, and it's a common one. We're often conversing with AI verbally or by writing text messages, for example. But we might also want to think about how could we use AI to generate images. There are lots of image-generating AI out there, and there are many different techniques that AI uses in order to generate media like images. And today, we'll explore just some of these techniques that have become popular for use in AI to be able to generate images. And let's start with the example of a generative adversarial network. So what is a generative adversarial network? Well, it's a neural network architecture that's used to help us generate new kinds of data. In particular, it's often useful for generating images. So let's imagine, for instance, that you wanted AI that was going to be able to do a good job of generating images of flowers, for example. Here's a real photo of a flower. And maybe I want AI to be able to generate new images of flowers for me. How could we go about doing that? Well, let's take a look at an example of what the generative adversarial network architecture might look like to get an understanding for what's going on here and how we could train an AI to generate pictures of flowers. All right, so I have here a representation of a generative adversarial network, which we can use to do something like generate images, for example. And a generative adversarial network is made up of two parts, two components. You can think of them as two major neural networks that are part of this system. I have the generator over here, and the generator's job is to generate new data. It's going to generate images, in this case, ideally, of flowers. So I want the generator to be able to generate flowers. And then meanwhile here, I have a discriminator. And the discriminator's job is that it is a neural network that is trying to tell the difference between a real photo of a flower and a generated photo of a flower. It's going to try and tell apart an actual photo from one that was AI generated. And of course, initially, when I first set up these neural networks, neither one of them is very good. Neither the generator nor the discriminator is very good at its job. But we could try it out. We could see what happens. So in order to test out this discriminator and train it, I need some real data. I need some examples of real photos of flowers. And I have here a whole bunch of training data, a whole bunch of different photos of flowers. So I'll go ahead and just start with one of them. So here is a real photo of a flower. And I'm going to go ahead and give it to the discriminator. And the discriminator's job is going to be to tell whether it's real or whether it's generated. And it'll tell us that via this light over here. The light is going to turn green if it thinks that it's a real photo. And it's going to turn red if it thinks it was an AI-generated photo, for example. So we'll go ahead and take this photo. We'll give it to the discriminator. It is a real photo, and we'll see what happens. We'll go ahead and run the discriminator. We'll see what happens to the light. And OK, the light turned red. That means the discriminator thought this was an AI-generated photo. That was wrong. This was, in fact, a real photo of a flower. But at least this gives us some way that we can now train the discriminator, that over time, we can train the discriminator to get better. And in this case, it's going to learn from its mistake. So I'll go ahead and open this back up. Here then was the photo. This was the real photo that I gave to the discriminator. And this time, it didn't do a very good job. It thought that it was AI generated. In fact, it was real. But we're going to train from that. We're going to learn from that experience. And the discriminator is going to get better at telling apart real photos from AI generated ones. So we could try again after we've trained the discriminator a little bit more. Here's another real photo of a flower. And we'll go ahead and bring this photo into the discriminator. And we'll let the discriminator run. We'll see what happens. And OK, this time the light turned green, which means that the discriminator correctly identified that this was, in fact, a real flower photo, not an AI-generated one. So OK, that seems to be working. OK, and that's the discriminator's job, to try and tell apart a real photo from one that was AI-generated. But now let's turn our attention over here to the generator. The generator we haven't touched at all yet. The generator's job is going to be to generate photos of flowers. And initially, this generator is probably not going to be very good, but we'll go ahead and see what happens. It hasn't been trained at all yet, so initially, it's probably just going to do a pretty bad job, a pretty random job of trying to generate something that looks like a flower. But we'll see the generator is doing its generating now, and we'll see what kind of output it's able to come up with. All right, we've gotten the generator to generate something. And here's what it looks like. And I would argue this does not look very much like a flower. This did a pretty bad job of generating an image of a flower. But that's probably what we could have expected. We haven't trained the generator to generate images of flowers. So it's not going to do a very good job. And we could see, what does the discriminator think of this photo? Does it think that this is a real photo of a flower or a generated one? So I'll go ahead and open up the discriminator. We'll give it this image, the image that was produced by the generator, and we'll see what happens. We'll go ahead and run the discriminator. We'll let it run. We'll see what happens. And OK, the light turned red. The discriminator was able to identify, you know what, that was not a real photo of a flower. That's not too surprising. I'll open this back up again. That's not surprising at all, because this didn't really look anything like a flower. The generator didn't do a very good job. But just like we were able to train the discriminator based on its mistakes, we can also train the generator based on its mistakes. Every time the generator generates an image, and the discriminator is able to tell, you know what, that was AI generated, that wasn't a real photo of the flower, well, then the generator learns what to do better next time. It learns next time how to adjust very slightly to try and do a better job of fooling the discriminator. So the generator is trying to fool the discriminator, and the discriminator is trying not to be fooled. And so over time, as we train the generator more and more based on that output, we can try again, and we can see what happens. We'll go ahead and let the generator generate yet another image. And we'll see if this time, maybe it'll be able to do a better job of trying to fool the discriminator. So the generator is doing its generating. We'll see what it comes up with. And all right, here's the output from the generator. And if I look at this, I can say, you know what, it still really doesn't look like a flower, but at least it's a little bit closer. We have some semblance of a color in the middle and maybe something that looks vaguely like the colors of petals on the outside. And how is the generator learning to do this? Well, it's learning based on its mistakes. It's learning, if I wasn't able to fool the discriminator last time, let me try something different. And we'll see what happens now. We'll go ahead and give this photo to the discriminator and see what it does with it. We'll let the discriminator run and see what it says. And this time, the light turned green, which means the discriminator was fooled. It thought that that was a real image of a photo, even though if I open this back up again, you and I can probably tell this is not a real photo of a flower, for example. But both are now learning from this experience. From the generator's perspective, it learned, you know what, this was closer to a flower than that image we saw before. So next time, we can do more things like that. And the discriminator is learning, I need to be able to do a better job of telling apart images like this from a real photo of the flower. And so we're going to keep learning. We're going to keep up this process. And maybe we need to give some more real data to this discriminator to let it do a better job. So here then is a real photo of a flower. We'll give it to the discriminator and see what happens. We'll let the discriminator run, see if it thinks it's real or fake. And it learns that, yes, in fact, this was a real photo of a flower. So it did a pretty good job there. Go ahead and open up the discriminator again and remove this photo. And now let's go ahead and let the generator try again. We'll let it run and see what it's able to come up with. And again, this process just repeats again and again. This is an adversarial situation where both models are trying to fool each other. The generator is trying to come up with images that fool the discriminator. The discriminator is trying to make sure it doesn't get fooled. And so each one's success is a mistake for the other, and they each learn from their successes and learn from their mistakes. And eventually, the generator starts to do a better and better job of generating things that look like flowers. And we'll see, this is starting to look a lot more like a flower. Is it good enough to fool the discriminator? We'll find out. We'll go ahead and provide this image to the discriminator, and we'll see what happens. We'll see what color it turns. In this case, it turned red, so it didn't do such a great job. But again, we can keep training this. We can keep letting this process go on and on again. We'll maybe let the generator run one more time, see what it's able to come up with, and see if it's able to come up with something that's a little bit better. And in practice, this doesn't just happen a couple of times. It happens many times. And computers can repeat this process very quickly, continuing this training process again and again, until eventually, by the end of the process, the generator starts to do a pretty good job of learning to create things that look like a real image of a flower. And so at that point, we might be able to say that our generator has learned how to generate things that look like a real flower. And so I think we'd stop there. I was going to do one more discriminator thing, but it was starting to feel like it was running long, so I didn't want to keep going with that. All right, so I have here a representation of a generative adversarial network whose purpose is to be an AI system that can generate images of its own. And in this case, we're going to be trying to generate images of flowers. And the way a system like this works is that it's made up of two parts. Think of this as two separate neural networks. I have one neural network here, which we call the generator, and one neural network here called the discriminator. And each one has a different job. The generator's job is going to be to generate images of flowers in this case. And the discriminator's job is to be able to tell apart a real photo of a flower from an AI-generated photo of a flower. And these two parts are going to be working against each other, and we'll see in a moment how that works. But let's start over here with the discriminator. The discriminator needs to learn what a real photo of a flower looks like, so it can tell that apart from something that was generated, like generated via the generator. And so we might train this neural network over time with a bunch of data. So for example, I have here a real photo of a flower, and this might be training data for the discriminator. So I'm going to go ahead and open up the discriminator. We'll give it this image and let it do its analysis. And what's going to happen is this light here is going to turn green if the discriminator thinks that it's a real photo of a flower. And it's going to turn red if it thinks it's an AI-generated photo of a flower. And so we'll see what happens. This is a real photo of a flower. We'll let the discriminator run. We'll see what color it turns. And in this case, it turns green. So the discriminator was correct. It correctly identified that this image was a real photo of a flower. So I'll go ahead and open this back up, take this image out. And this time, let's move over to this generator here. So the generator's job is going to be to try to generate images of flowers. Now, initially, when we first start, the generator has no idea how to generate a photo of a flower. It doesn't even know what a flower looks like. So odds are its first try probably won't be very good. But we'll see what kind of output this generator is able to come up with. And we can see that in this case, it really doesn't look very good. You and I can pretty easily tell that this is not a photo of a flower. It's just kind of a random blob of color. But let's see what the discriminator thinks of this. So we can take the photo that the generator created, and we'll feed it into the discriminator. And we'll let the discriminator run, and we'll see what it says. Does it think it's green, real, or red AI generated? And in this case, yeah, the light turned red, which means the discriminator was correctly able to tell that this photo was, in fact, AI generated. It's not a real photo of a flower, perhaps unsurprisingly, because if I open this back up and look at the photo, we can pretty clearly tell this is not a photo of a flower. But importantly, the generator is able to learn from that mistake. Anytime the generator generates something and the discriminator can tell that it's AI generated, well, then the generator learns what not to do next time. It learns a little bit from that experience so that next time it tries to generate an image of a flower, maybe it'll do a better job. And it might take a lot of tries for this to happen, but ultimately computers can do this kind of process very, very quickly. So again and again and again, the generator can try generating images. And hopefully every time the discriminator can tell it was AI generated, the generator gets better. And then eventually it starts to get better itself as the generator at producing something that looks a little bit like a flower. Now you and I, we can probably still tell this is not a real photo of a flower. But it's starting to look like one. It's got a little bit of color in the center and something around the edges that might be believed as petals. So this is starting to do a better job. Our generator is getting better. Let's see what the discriminator thinks of it. We'll go ahead and put the photo into the discriminator, let it run, and see what happens. And in this case, it turned green, which means the discriminator was fooled. The discriminator thought that this was a real image of a flower, when in fact it was AI generated. So I'll go ahead and open this back up. This photo was able to fool the discriminator, and that's news for the generator too. The generator now learns that whatever you did, this was good. Start to do more things that look a little bit like this. But now the discriminator is going to need to get better too. It needs to learn to do a better job of telling apart real from generated. So it too is learning from its mistake, and maybe it needs a little bit more real data, so we can give it one more real image of a flower and see what it does with it. So the discriminator is learning from its mistakes as well. And in this case, the discriminator learns that, yes, this is in fact a real image of a flower, so it was successful this time. It can learn to do more of that kind of thing in the future. So I'll open this back up. So ultimately, both of these models are working against each other. The generator keeps trying to come up with things that are going to fool the discriminator. The discriminator keeps trying to tell the two apart. And every time each one succeeds and the other fails, they learn from those successes. They learn from those failures. And if we do this again and again, keep repeating this process of trying to generate, trying to discriminate, each one learning every time it's correct, every time it's wrong, eventually we can get a generator that does a pretty good job at generating things that look like flowers. Over time, it gets better and better at coming up with things that look realistic. And of course, it might take many tries, but eventually, the generator is able to come up with something that really looks like a real flower. And at that point, we don't really need the discriminator anymore. We can just use this generator as a neural network that has now been trained, that has now learned how to produce things that look like real images. That's that. So that then is what it might look like to use a generative adversarial network to try and train AI to be able to generate images. We have these two parts, the generator, whose responsibility is for trying to generate new images. And then we have this second part, this discriminator, whose job it is to tell apart AI-generated images from real images. And we need this real image training data set to train the discriminator. And so what the discriminator ends up learning to get good at is it learns to get good at taking an image that was from the generator and then using that and identifying that that image was, in fact, AI-generated. And meanwhile, when the discriminator gets a real photo, like an image of an actual flower, well, then the discriminator will be able to say that, yes, in fact, it is real. And it doesn't know that from the beginning. It learns that by being trained. Every time it sees a real photo, every time it sees a generated photo, and it gets it right or it makes a mistake, it can learn from that and get better at trying to discriminate in the future. And meanwhile, the generator is getting better too. Every time it fools the discriminator, it learns what to do more of in the future. Every time it does something that doesn't fool the discriminator, it learns what to do less of in the future. And by the end of it, the generator can start to do a pretty good job of generating images that do, in fact, look real. And so this kind of generative technology can allow AI to produce images, but it also raises some important societal questions, questions around, can we trust the things that we see in images and video and audio too? And we have this concern around deep fakes. So what is a deep fake? Well, the deep comes from this world of deep learning, using these deep multi-layered neural networks to be able to generate data. And the idea is that now these deep neural networks have the ability to generate images and audio and video that is actually fake, that looks real, but that might be hard for a human to be able to tell that it is, in fact, AI generated. And so it's the type of thing where previously, if you saw a video, you might be able to trust that it actually came from a real camera. But now we need to start to doubt that. We need to start to question for the things that we see, could they, in fact, have been generated by AI instead? And generative adversarial networks are only one of the strategies that are used for trying to generate data. There are other strategies that often can do an even better job of trying to construct things that look real. And we'll talk about some of those other strategies too. So one common approach to trying to build generative models is the idea of a variational autoencoder. And this sounds a little bit fancy. What is a variational autoencoder? But I'll talk through the architecture at a high level and give you a sense for what it is that these kind of models might be trying to do. The essential idea of these autoencoders is that they also have two parts. They have an encoder and they have a decoder. And what is the role of each? Well, the encoder's job is to take a whole bunch of input data that might have many different parts to it, many different numbers to it. And the encoder's job is going to be to try and compress all of that data into a smaller, more compact representation. Take many numbers and turn them into fewer numbers. And so the encoder is going to encode this big input into something a little bit smaller. And then the decoder's job is going to be to try to do the reverse, to take this intermediate step of this compressed, more compact representation and reverse it and try and come up with whatever the original input was, or as close as you can get to the original input. And you might wonder, well, how do we use this to generate images, for example? And we'll get to that in a moment. But for now, let's focus on this mechanism of how do we encode something big into something small, such that we can later decode it back into something that looks a little like the original. So let me give you a simple example, just using some simple numbers. Here might be an example of some input. In this case, I have the inputs 4, 6, and 8. And imagine that I have a whole bunch of these inputs. These are all inputs that have 3 numbers each. So here's 4, 6, and 8, and then 6, 9, and 12, 10, 15, and 20, and so forth. And what I'd like to do is take these 3 values and compress their representation into just a single value, such that later I can reconstruct the original input. I want to learn an algorithm that takes 3 value sequences and encodes them as a single value, and then a decoding algorithm that takes that single value and turns it back into the 3 values. And in order to do that, in order to be able to do that well, to be able to encode things and then decode them, I'm going to need to study this data and identify the patterns, identify how it is that this data works, what are the patterns that define data of this form. And if I look at this data, what I might notice is that within each unit of data, this one here, the second one here, the third one here, and the fourth one here, the values that we have are all multiples of something. Like in this column, I have all of these multiples of 2. If I do 2 times 2, I get 4. 2 times 3, I get 6. 2 times 4, I get 8. Whereas in this column here, all of these values are multiples of 3. So 3 times 2 is 6, and 3 times 3 is 9, and 3 times 4 is 12. And then I have multiples of 5, and I have multiples of 7, for example. So if I was going to try and describe these 3 numbers using just a single number, I might try and say, all right, what are they all multiples of? And maybe we could do that and say, all right, I'm going to represent these 3 values using just the number 2, or just the number 3 in this case, or just the number 5, or just the number 7. And I've encoded this in such a way that hopefully if I remember the pattern, that this is going to be 2 times whatever that value is, and 3 times whatever that value is, and 4 times whatever that value is. Well, now if I get rid of all the inputs, and I only show you this encoded representation, could you reconstruct the original input? Could you figure out what the original was? Well, if you remember that pattern, it was times 2, and then times 3, and then times 4. Well, then I could say, all right, for this one, times 2 would be 4, times 3 would be 6, times 4 would be 8. And I could do that for each of them, and then reconstruct something that looks like that original input as well. So this then is the idea of this encoding and decoding process. Take a lot of data, compress it down, and then into some kind of code, and then uncompress it in order to decode it back into the original. And in order to do so, I need to do something about identifying the patterns that happen to show up in this data. And in reality, I might not be able to construct this input back exactly. In this case, all the numbers happen to be really clean, so it was really easy for me to do the encoding and decoding. But even if the numbers were very slightly different, such that I could get a general sense for the pattern, I might not be able to decode it perfectly, but I could at least do a pretty good job. And so let's come back to this image then. Big input, encode it into something smaller, then try to decode it back into the original. Why is this useful for building something that can generate images? Well, imagine if the input to this encoder-decoder model was in fact an image. Imagine like all of the pixel values of that image. And the encoder and decoder are these big neural networks, for example, that are trying to encode and then decode that image. We're taking some big image, and then we're trying to describe that image using just a couple of numbers, some arbitrary numbers or numbers that represent that image in some way. And then the decoder takes those numbers and is able to turn them back into something that looks like an image. And so now if I have a model like this, an encoder and decoder that are used for, say, image data, well, what happens if I then get rid of the encoder and I just focus on what it is that this decoder is doing? Well, what the decoder is doing is it's taking some small sequence of numbers, and it can turn that small sequence of numbers into something that looks like an image. That's what it was trained to do. And so what I might be able to do is just sample a whole bunch of numbers that I could potentially choose randomly, or maybe choose a little bit more intentionally. But I just pick some numbers, feed them into the decoder, and the decoder can take whatever numbers I gave it, and then use that to generate something that looks like an image, maybe an image that we've never seen before, some new image, because it didn't actually come from some real image that was encoded. I just picked some values here in the middle and said, decoder, go ahead and try and construct an image. And if what the decoder has learned to do is construct images based on that encoded representation, well, then now this might be able to do a good job of generating images as well. So a couple different strategies here for how we might be able to generate images. And one of the most popular tools nowadays for trying to generate new data, generate images, and other kinds of media is something that we call the diffusion model. So what is a diffusion model? What is the idea here? Well, let's imagine for a moment that I asked AI to generate an image, but I didn't train it at all. I just said, go ahead and generate an image of something, try and make it look as realistic as possible. What would AI do? Well, if it had no training data, nothing to work with, it would have nothing to help guide its process. It wouldn't know how to generate an image. So what it would generate is probably just something that looks like this, just static random noise, where each pixel here is just like some random color, for example. This doesn't look like anything, but this is what AI might come up with if it wasn't trained. It's really easy to write an AI that can generate something like this because all the pixels are just totally random. It's much harder to build an AI that can come up with something realistic, something like this photo, for example, this photo of ducks swimming in a pond. So now we can imagine this is our goal, whereas it was really easy to get AI to generate just that noisy image of just static. And we can think about those two images together and say, could we take this image of a duck, or of multiple ducks swimming in a pond, and turn it into that image of just noise? And this would be reasonably easy to do. We could take this nice-looking image and turn it into that noisy image just by adding a whole bunch of noise to this image, add a whole bunch of random pixels, keep changing them randomly a little bit at a time or a lot at a time until eventually you end up with something really noisy, really staticky, something that looks like the thing at the right. It would not be hard to develop a computer system that could take a real image on the left and turn it into something on the right. The idea then for a diffusion model is to learn how to reverse that process. If we can learn to do the process in one direction, take the real image and turn it into that noise, could we learn to do the opposite? Take this noisy image and denoise it, remove the noise, in order to turn it back into something that looks like a real image. And how might that be possible? What would that process even look like? Well, let me give you a simple example. Here's a 4x4 grid of pixels. It's pretty clean. I've got red over here on the top and blue over there on the bottom. And let me add a little bit of noise to this image. For each of the pixels of the image, I'm just going to pick some random amount of color values to add or subtract from it. I'm going to make this image a little bit noisier. And here's what it looks like now. I've added a little bit of noise to the image. But you could probably still tell that, the top half seems to be red and the bottom half seems to be blue. And so you could imagine trying to learn how to remove the noise from the image. If I ask you to remove the noise from the image, you might be able to do a pretty good job of guessing that what it looked like before the noise was probably red on top and then blue beneath it, something like that. So you might imagine some way that this kind of thing could be possible. But of course, this is possible because I'm only removing a little bit of noise. It's not like the image was totally noisy and then I'm removing all of it at the same time. But what we've learned here is that if we go step by step, removing a little bit of noise, that might be a little bit easier for a computer to be able to do. And so here then is the idea of what we're going to do with the diffusion model. We're going to start with some training data. Our training data is a whole bunch of real images. And we're going to take that training data with a whole bunch of real images, and we're going to iteratively add noise to that image. Step by step, add a little bit of noise to the image. So I'll go ahead and try this. I'll add a little bit of noise to the image. It starts to look a little bit grainier. The colors aren't quite as perfect. And I'll do that again. And we'll keep repeating this process again and again, each time adding a little bit more noise to the image. We'll do it again and again and again. And each time we're starting to see less of that original information that was present in the image and more just noise that happens to be populating the image until pretty much we can't reconstruct any information that we can visibly see from that image. It looks pretty noisy, just like this. And so now I have all of these steps that went from my original image that looked real, adding noise bit by bit until we weren't really able to see anything anymore. But each one of those steps was really just us adding a little bit of noise into the image. So if I just take two of the images, for example, each noise step looked like taking the image on the left, which already had a fair bit of noise, and adding a little bit more to make it a little noisier. And that one step is going to be what will train AI to be able to reverse in this case, to be able to say, can we go in the opposite direction, go from a lot of noise to a little bit less noise? And again, we do that via data, by giving the computer lots of examples of images, by adding noise to each of them, and then training AI to be able to remove that noise. It might try to remove that noise and not do a very good job, but it learns what the correct answer is because it has access to the training data, that real image that we had to start with. And each time it's able to learn from that data. It's able to do a better job of learning. What does it look like to remove noise? To be able to remove noise, you probably need to learn things about the patterns of what objects in the real world tend to look like, how colors tend to transform across a surface. You learn things about lighting and about shadows and about edges of objects, for instance. And if you do this enough, you can start to get a sense for how AI might be able to reverse that noise process. And so what could we do at the end of this? Once we've trained AI using a technique like this, well then, we could just give AI a bunch of noise and say, go ahead and try and denoise it. Go ahead and step by step remove a little bit of noise and try and make it increasingly look like some kind of real photo. And so one step at a time, we might try to remove some noise, remove a little bit more noise, and repeat that again and again and again. And each time we get closer and closer to something that starts to look real, until eventually we get back something that looks like a real image. And it might not be this specific image. It might be some other image, for example. But the idea then is that AI can learn to produce things that really look real. Now, when we generate an image, usually we don't just want to generate some random image. Usually there's something specific that we want AI to generate, like generate an image of a flower, for example, or generate an image of a duck. And so we might extend this idea by, instead of having the data set that we're training AI with just be a bunch of images, those images might be labeled, say, with a description of what's inside of that image. So we might label this image with a caption, something like photograph of ducks swimming in a pond. And so what AI could learn then is it could learn how to remove the noise from an image by paying attention to particular words, using some of those language model techniques. If it knows what an image of a pond looks like and what an image of ducks look like, then we can use that information as we're trying to figure out what this is a photograph of. As AI is trying to take away the noise from the image and generate something that looks like this, it can use that text as a guide for it. So it doesn't just generate something random. It can generate something that looks like whatever we wrote as the description, whatever was the goal for what we wanted AI to generate in this case. So there then are a number of different strategies that AI can use for trying to generate images. We've looked at a bunch of different architectures. They have their various strengths and limitations in terms of how accurate and how sharp they might be able to be and how well we can understand the meaning of what's encoded inside of an image, for example. But these all are strategies that could be used to generate images. But images are just one example of the type of data that we might want generative AI to be able to produce. Another thing might be speech synthesis or audio generation a little bit more generally. Like if we want AI to be able to produce speech or to produce sounds, what might that look like? Well, we've talked about sound a little bit before in this class. And the form that sound takes is sorry, I missed a slide there. I'll go back. So I'll go back to right before I say we've talked about sound a few times in this class. All right, so we've talked about. So we've talked about sound a few times in this class now, and we've talked about language in this class as well. So what are the challenges that come up when we're trying to get AI to be able to generate sound that sounds like human language, for instance? Well, one thing to be aware of is that it's not as easy as just mapping every letter or every word to what sound it corresponds to. There's some ambiguity when it comes towards language as well. For instance, if I took this phrase, take a bow, versus a phrase like this, tied with a bow, these words have the same letters, B-O-W, but they're pronounced in different ways because they show up in different contexts. And you might imagine that if you wanted AI to really learn how to emulate human speech, you would have to deal with differences in pacing and differences in tone and all sorts of different factors that contribute to what it is that human language actually sounds like. So what strategies could we use for trying to get AI to be able to generate language, to be able to generate sounds and speech? Well, one strategy is called concatenative synthesis. Concatenate just means put a whole bunch of things together. And the idea behind concatenative synthesis is that what we would do in advance is just record a whole bunch of really short audio clips of like different sounds that might appear in language. And if I had a whole bunch of different sounds, well then, if I knew what word I was trying to say, I could write a program that might stitch those individual sounds together and try and figure out what sequence of sounds would make sense. But that can often be a challenging thing to do because it depends on how many sounds you have recorded in advance, and it makes a difference in terms of the differences in tone in the English language, where it might be hard to replicate something that feels accurate. It might not feel very natural. And if you've tried AI speech generation in the past, especially years and years ago, often the voices didn't sound a lot like humans. They sounded very monotone. They sounded very robotic. They weren't doing a really good job of sounding natural. And so what other approaches could we use? What other strategies could we use for trying to train AI to be able to understand and produce sounds? Well, remember that sound is really represented as a wave that looks a little something like this. And remember that computers represent that wave via individual samples, little snippets of time, and measuring the value of that wave at a particular point in time. And so if we were to do that, we might get something that looks like this. This is what a computer might have representing some piece of audio, for example. And the reality is it's going to look messier than this. It's going to be a bunch of different values at different heights, a bunch of different frequencies mixed together. But these then are just samples. These are just individual numbers, and we have a sequence of those numbers. And what can we do when we have a sequence? Well, we can start creating prediction problems, like trying to predict the next item in the sequence. We saw this in the world of text generation, where when we were trying to have AI generate text of its own, it started with a whole bunch of text tokens. And what it was trying to do is predict what is the text token that I think comes next. What is the next word after this? What is the next word after that? Well, we could imagine trying to do the same thing with an audio waveform, something like this, where we say, you know what, starting with this very first sample of audio, can you predict what you think the sample of audio that comes next is? Could you predict the second one? And from the second one, could you then try and predict this third sample of audio that comes after that? And from the third one, could you predict the fourth one? And so on and so forth, every time taking some audio and trying to predict what is the audio sample that's going to come next after the ones that previously appeared in the sequence. And how could you train AI to do something like this? Well, again, we'd have to give AI some training data. If we gave AI a whole bunch of different audio clips of what it is that human speech sounds like, for example, we could set up some training problems where we could give AI some examples of samples of audio from some training data and say, can you predict the piece of audio that comes next? And what is the next piece of audio that comes after that? And we can judge whether it gets it right or wrong by comparing it to that original training data. So AI could learn over time how to predict the next part of the audio waveform, the next sample of audio that might come next. And sometimes we might not use samples of audio directly. It's certainly possible to do so, but we've learned already that these samples can often be quite messy and that we have many frequencies that are woven together. So we've talked about other techniques in audio, like spectrograms that map out for each unit of time what are the frequencies that are more or less popular. So you could imagine performing a prediction task that way too, where maybe AI is trying to predict what is the next piece of the spectrogram that comes next. What are the frequencies and how intense are they at any given moment in time? And that might be a way you could generate audio as well. Or maybe rather than generate one sample of audio at a time, maybe you combine multiple samples together into something like an audio token. In the same way that we were able to take the English language and divide it up into tokens in different ways, where you could go character by character, or you could go word by word, or some subword, some piece of a word, and then some piece of a word. You can imagine doing something similar for audio too, that rather than predict every single one of these individual samples, you could divide audio up into smaller chunks, little tokens of audio that might be predicted, that AI could learn how to do that chunking and how to generate them, so they wouldn't need to be pre-recorded in advance like some human recording every sound, but AI could figure out what are the individual units of sound that we care about, and then how might we try and predict what little unit of sound might come next. And so the idea then is that by taking these generation tasks about AI trying to generate data and turning them into prediction tasks, we can use the techniques we've talked about AI making predictions to be able to generate new data. It can try and predict what word is going to come next in a sequence. It can try and predict what piece of audio is going to come next in some audio clip, for example. It might try to predict whether an image is real or AI generated. But by taking these problems and turning them into prediction problems, then we have a chance at trying to solve these very difficult problems of getting AI to be able to generate data. And so next time, we'll continue this look at these difficult problems that AI might try to solve and bring those problems into the physical world too, thinking about how AI might deal with and navigate the physical world and figure out how to move about the physical world as well. So that's coming next. Thanks for joining us, and we'll see you next time.